Assalamu alaikum warahmatullahi wabarakatuh. Welcome back again for a new topic for this module of rigid body motions and spatial transformations. In this video, we will learn more about the homogeneous transformation and how we can combine the position and orientation of our rigid bodies in one matrix. Okay. Here we will consider our problem and how we can solve this problem. Okay. Here we have reference frame B, and we have a point P represented in frame B. Okay, and we could call this as P with the superscript B. Okay. This point, we want to represent this point with respect to this frame. So if we have the information of this vector, okay, and we want to find this vector P with superscript A as a function of this vector, okay, P represented in B reference frame. Okay, so we can use this vector which represents the position of the origin of the reference frame B with respect to the frame A. You can call it as P AB with respect to A. Okay. From the linear algebra, okay, we can remember this with the summation of vectors. We can find this final vector PA is equal to this vector plus this vector PAB A multiply plus P in reference frame B. Okay, but in order to make all of these summation with respect to the same frame, we have to find this vector with respect to frame A. So I have to multiply it by rotation matrix BA. Okay, the rotation matrix BA. Okay, we can see that this is we can call it as a affine relationship. Okay, so we can call it as a affine relationship, okay, or relative relationship. Here as a function, here we have B as a function of PAB and P, okay, with respect to B. But in order, as we learned before, the linear relationship is easier, okay, to understand and easier to manipulate rather than this expression. Okay, especially if I have a successive movement. Okay, so it is very easy to find a matrix that can be used to convert any position and orientation with respect to other frame. Okay, so we will use what you can call it as homogeneous transformation. We will add here one. Okay, so it is a temporary value. Okay, and if I if I make a multiplication and summation multiplication of this vector, of this matrix with this vector, we will obtain the same result. Okay, so we have to multiply firstly this row with this column, okay, which will provide this value, and if we multiply, yeah, 0t is a vector 3 by 1. If we multiply this by b, it equals 0. 1 multiplied by 1 equal 1. So here we have obtained the 1. So it is a temporary value in order to obtain a 4 by 4 matrix. Okay, in order to obtain a 4 by 4 matrix, and when we multiply a 4 by 4 matrix by any 4 by 1 vector, we will obtain another vector. So, okay. So, how to use the use of homogeneous transformation, describe the relation between two reference frames, relative pose. When we use this term pose, this term means position and orientation. Pose transform the representation of a position vector, applied vector starting from the origin of the frame, from one frame to another frame. It is a root translation operator on vectors in the three-dimensional space. It is always invertible. Okay, it is always invertible. The inverse of this TBA equal TAB can be composed. Okay, composed or compound for any successive movement or of the frame. Okay, so this we will consider it the foundation of the forward kinematics and inverse kinematics, because in forward and inverse kinematics, for each joint here we have a frame, we have a homogeneous transformation matrix, and we want to find the relationship between the position and orientation for the end effector to the world frame, for the tool frame to the world frame, Okay, so here we can, for the same expression, yeah, we can consider two special cases. The same frame are parallel, so there is no any orientation. So in the homogeneous transformation, we can see that this rotation matrix is equal identity, equal 1. Okay, if there is no any translation, okay, if we don't have any here, this vector, okay, r o dash, or if from a to b, okay, if we don't have any translation, so the translation vector equals 0. Just we have rotation or changing in orientation. Okay, so for translation only, the rotation matrix will equal identity matrix. Just the diagonal has 1 1 1 3 1 1. Other elements has 0 values. Okay, here if we have just rotation, here we will have a vector 3 by 1 equals 0. Just we have a rotation matrix. Okay. Here an example: describe frame B relative to frame A if the origin of B is positioned minus 2, 3, and 5 in XYZ. Okay, so here we have the translation. and B is rotated 30 degrees above the axis, and here this is the rotation matrix, this 3 by 3 matrix. As simplicity, in order to simplify and minimize the size of writing here, the size of words, just we will replace any cosine with C and any sine with S. Example on translation only. Frame B is translated 10 units in X and 5 units in Y. Find ABFBB. Just we will add this vector to the vector of translation. Okay, you can solve this problem. Example of rotation only. Frame B is rotated relative to frame A about Z axis by 30 degrees. Find RBA. Find BAFBB is 0, 2, 3. Okay, just similar to our previous discussion. Okay, we have a rotation. We have to multiply the rotation matrix with vector P B to find PA. So we can use the same principle to solve this problem, to practice with your hand. Okay, this problem. Example here on translation and rotation. Frame B is rotated relative to frame A about Z axis by 30 degrees, then translated 10 units in XA, 5 units in YA. Here this translation. Here this the rotation. Define frame B relative to frame A. Here we have to define. Then find PAFBB 370. Just we have to multiply after adding one here, adding one. Okay, for homogeneous transformation. This is a temporary addition. Okay, in order to use the matrix multiplication. After that, we will extract this one and find the PA. Okay. Here example on translation operators. Vector P1A translated 10 units in XA, 5 units in Y. Find the new resulting vector P2A. Just we will add the translation vector. Also we have class exercise. Rotational operators. Also operators. We multiply the operators by the old vector to find the new vector, and also for general transformation operators we can do the same thing. The same thing. Okay. Also here, okay. There is here important notice that the inverse of homogeneous transformation is not equal the transpose, like the rotation. Okay. Okay, so here we can see in a simple method how we can find the inverse of the homogeneous transformation. Okay, the inverse of the homogeneous transformation. As we remember, the vector PA in frame A, okay, for the same point equal the vector P E multiplied by the rotation matrix plus the translation vector PAB. Okay, on the same way, PB is equal the vector P with respect to A multiplied by the rotation matrix plus the translation vector between the two between the two frames, but here it will be from B to A. Okay, from B to A. Okay, so if I want to write this expression in terms of the rotation matrix B A as before, okay, and also with the same translation vector P A B, okay, the first thing is to find this vector with respect to frame A. So I have to multiply by RPA, but we have to remember this vector is moving from P to A. Okay, this vector here, this vector is moving from B to A. If I want to find this relationship in terms of PAB, so I have to invert it. Okay, so in order to invert it, just I have to add a minus. Okay, thus we have to add a minus. So this term equal this term. Also, I have a PA with this rotation, but I want it in terms of RBA, and as we know, RAB is equal RBA transpose. Okay, so from here we can find that we can from this expression we can find the inverse homogeneous transformation. The inverse homogeneous transformation, this will represent the translation vector. Okay, and this term RPAT multiplied by PA will represent the rotation matrix, because here we have to represent this vector from frame A to frame B. Okay, so here we have a symbol conversion relationship between direct homogeneous transformation and inverse homogeneous transformation. Here we can increase our understanding by doing this simple example. Frame B is rotated relative to frame A about z-axis by 30 degrees and translated 4 units in x-axis and 3 units in one axis. Find the transformation matrix that describes frame A relative to frame A to frame B. Whereas the information here is for frame B. This information describes the relationship of homogeneous transformation of that describes frame B relative to frame B relative to frame A. So firstly I have to find the direct transformation matrix TBA, okay, as before. After that, after I finding this information, we can find by using this formula. Okay, we can find TAB, okay, the transpose, yeah, and and the minus of transpose of the rotation matrix multiplied by this vector. Okay, so we will convert any columns, any rows. Okay. So as we said earlier, we have to just to implement this method and this is this expression in order to find the inverse of the homogeneous transformation. And as a note, as we said before, the above inverse of the transformation is not the same as the transpose of the transformation. Okay. Now let's go ahead, move towards another topic, which is the compound transformation. The compound transformation. Okay. Here as a review for the homogeneous transformation. Okay, we have a relationship for position and orientation for any frame with respect to another frame. Okay, which contains the rotation matrix and position vector and scaling temporary value. Okay, and as we said before, is we use if I have this is the simplest way to achieve the simple compound transformation from one frame to another. If I have a multiple frame and I want to find a vector in frame 4, in frame 0 with respect to frame 4, okay, it is so easy to make a multiplication rather than use a fine method. It is so complex. Okay, a fine versus linear computations. Okay, so here we have the common rotation. The rotation of the next frame about the old or current frame. Okay, this is the common case composite homogeneous transformation. Just we multiply post multiplication. Okay, if I want to find the relationship between the reference frame of 2 with respect to 0, just I have to multiply A21 with A10, chain product of successive coordinate transformation matrices. Okay, this is the common. But what if the case? What if the case is to move around a fixed frame? For example, fixed frame which is x0, y0, z0. Okay, the x1, y1, z1 moved around the same reference frame as z2, because here in the common case z2, y2, x2 moved with respect to x1, y1, z1 and so on. Okay, so here we have two different cases. Okay, before we talk about these cases, just here we want to make a look for this homework. Okay, because we have two methods. Okay, we can find the relationship between any frames with respect to other frame, either with the homogeneous transform multiplication or by inspection. We can use the inspection if just we have this symbol orientation. Okay, but if we have complex orientation, it is better to use the multiplication of homogeneous transformation. Okay, so here we have this example. Here we want to find I minus 1. Okay, for example, A1 to A0, A2 to A1, A3 to A2, also AI0, A10, A20, A40. Okay, here just we have example. We have here example. These dimensions are known E, D, C, A, B. Okay, just by inspection you can find A10. Just translation in this known dimension. Okay, and orientation, as we said, as we made in the first topic, position and orientation. Okay, so here a sample of answer, and you have to find the other value, the other answers for this question. So we can find the answer by observation based on the geometric interpretation of homogeneous transformation matrix. Now we will talk about the two cases of composite rotation matrix. Okay, so the composite of rotation is a sequence of finite rotations. Matrix multiplications don't commute. So the rules: if rotating coordinate OUVW is rotating about principal axis of OXYZ frame, and it is fixed, okay, then pre-multiply. Yeah, if we rotate with respect to one and fixed frame, the first frame, any successive rotation is around the same fixed frame. So here we will use the pre-multiplication. Okay, pre-multiply the resultant rotation with an appropriate basic rotation matrix. The second case, and it's the common case, if rotating coordinate OUV is about its own principal axis current, okay, any next rotation matrix is rotated about, or any next frames is rotating about the previous one, then we have to use the post multiply the previous rotation with an appropriate basic rotation matrix. Here as a homework, you have to prove it, okay? And you can find the answers in references. Also, there is two methods to prove to prove them, and we can see in the minimum representation. We can take a look at one of these methods. Okay, here we have example. We have to rotate about. Always the first rotation is about the fixed axis or y-axis. Then rotation about OW, so it is the next the rotation about the new frame, the rotation about OU, okay, it's the new frame. So this is the first rotation. Then I will make post pre multiplication. Then I will make post multiplication, because here the rotation around the current frame, the next frame rotated about the current frame, okay, or its previous frame, not the first, just the first frame or fixed frame. Okay, here we can make a multiplication and find the final result. Okay, here, in other words, here composite homogeneous transformation matrix rules of a transformation with respect to x, y, z, old frame used pre-multiplication with respect to new frame using post multiplication. Here also another example, rotation about ox, then translation of along ox axis, translation of d of a, then a length and d length along opposite axis, then a rotation about it. Here the answer is pre-multiplication. Okay, rotation about alpha, rotation, translation around x with a, translation along opposite axis with b, and finally rotation about it. So here the answer is pre-multiplication. Pre-multiplication. Okay. This the rotation matrix, translation around A, then translation with A along X, translation along Z with D. Here the rotation around Z with theta. Okay. So here we have to always remember, our homogeneous transformation. Okay, and always we have to remember each vector of this frame, okay, is represented in homogeneous transformation as a projection. We have to find its value. It's the projection of n, okay, of n vector with respect to x, y, z, for s vector with respect to x, y, z, and so on. Okay. Here a new example for this compound frame B is rotated relative to frame A about z-axis by 30 degree, and translated 4 units in x-axis and 3 units in y-axis. Frame C is rotated relative to frame B, TCB, about x-axis by 60 degree, and translate it 6 unit. 6 unit in x axis and 5 units in z axis. Find the position of P relative to A if PC equal 879. We have to relate this vector with respect to A. So I have to multiply these two homogeneous transformation and then have to multiply the result of this multiplication with the PC, okay, the PC homogeneous vector to find PA. Okay. So yeah, imagine here the importance of this compound homogeneous transformation for application, for moving robots, for aerial vehicles, for ground vehicles. Okay, so here if we have this movement, okay, we have here TBU, okay, TDC, we have TAU, TDA, we have here TDC. How we can find this? Okay, TCB, okay, as we can TDU, where this we can find any new relation from these given values. TDU is just equal the multiplication of this with this for this transformation matrix with this transformation matrix, and also TDU. Here this TDU also is equal to TBU, TCB, TDC. Okay, it is also equals by using the linear algebra. Okay, also it equals to this multiplication for this path. Okay, and so on. So because this equal to this, okay, you can just find the TCB. Okay, for linear algebra, in order to find this, we have to write to multiply each side by the inverse. I have to write here because the multiplication is not commutative. We cannot invert any multiplication. Just I have to multiply here with TDC inverse to eliminate this value. Okay. Then I have to multiply on this side by TBU minus 1. Okay, for both expression in order to find the TCB. Okay. Yeah, another example, find CA if the following transformation matrices are defined. We have TAB and TCB. How I can find TCA? The TCA is equal TBA multiplied by TCB. But I was given the TAB, so just I have to inverse it to find TBA, and we learned how we can find the inverse transformation, the inverse homogeneous transformation matrix. Okay. Okay. Now let's move to a new topic of minimal representation. representation of orientation, and this topic is exactly based on the compound transformation. Here we can see instead of using 9 elements inside the rotation matrix to represent the orientation, just we can use 3 angles, okay, by utilizing the compound transformation and find the relationship between this minimal representation and the traditional rotation matrix. As you can see here, after we discuss and after we learned the most important foundation of position and orientation, now we can